once we saw that particles could be viewed as waves, and this is mathematically predicting their probable locations, then these mathematical equations could be used to predict where an electron is likely to be. And so this is where we got rid of the idea that we have a ring and the electron is on it, or even a set distance from the nucleus, and we got more of a electron cloud type thing where this is distance from the nucleus in picometers. And we can see that for this electron, it's most likely to be 50 picometers from the nucleus, but you can see it could be at any point in time a lot further out or closer. So from that, these equations, we found that there are what we call orbitals, where that are regions in space where the electron has a high probability of being. There are different types of orbitals, and we use these letters to represent the different types. So the types are different shapes. And so like an s orbital is maybe like you would imagine an orbital being. But a p has two lobes. This is one orbital, it just has two lobes. D orbitals have four lobes, at least most of them do, kind of a clover leaf pattern. And the shapes get more complicated after that. Whenever you have p orbitals, you'll have them in sets of three. You'll have, this is one orbital with two lobes, left to right, front to back, and top to bottom. We're going to be doing electron configurations, which means you're going to tell where the electrons are in all of these low orbitals. So we could say the distribution of electrons in the orbitals. Okay, so we need to know which orbitals are in the different energy levels, and luckily there's a pattern. The circles represent an orbital. Each circle is one orbital. And remember how I said that p orbitals come in sets of three, the left to right, top to bottom, front to back? Okay, so that's why every time I write p, I have three orbitals by it. And then we have our pattern that first energy level has just S, second has S and P, third has S, P, and D, and so on. You gain orbital types, and there actually are more, but we won't need them when we draw we do our ground state electron configurations. And like I said, for the P's always come in sets of three. The S's, when you have S orbitals, there's always only one. Whenever you have d orbitals, they come in sets of five, and so on, 7 for the F's, and those are all that you will need, but there's that consistent pattern. Okay, we need to make sure we understand the language, what we're talking about when we say the sublevel name. For example, if I want to refer to those orbitals, I would call them the 2p orbitals, or I might call the whole set the 2p sublevel. Okay. Similarly, if I want to talk about those, I would call those the 5d orbitals. And I might say something like this, which gets confusing. There are 5, 1, 2, 3, 4, 5d orbitals. So you got to really watch the language and understand that this is a description of a sublevel or a group of orbitals. Okay, and like I just said, we call these sublevels when we're talking about this whole set. That's they come in sets of three. P's come in sets of three. So this is kind of how I would represent that sublevel. And why we call them sublevels? Well, I mean, it kind of makes sense that they're like within one level. When we talk about a level, we're talking about N, the principal energy level, and these are sublevels within that. So for example, the fifth energy level, here are 4 sublevels. These are all N equals 5, all part of the fifth energy level, and each one is a sublevel. And notice they have slightly different energies within that. So it's just that the energy of a principal energy level they're not all the same. There can be slight differences depending on what orbital they're in, which type of orbital that they're in. Okay, so just as we start talking about where the electrons go, we need some rules about where we're going to place them in all of the orbitals. So the first rule is that only 2 electrons can fit in an orbital, and they have to have opposite spins. So I listed here the sublevels. How many electrons can be in the 1s sublevel? Well, when you have S, there's only 1 orbital. And so since there's 1 orbital, you can have 2 electrons because it's 2 electrons max. The 2p sublevel can hold 2p, has 3 orbitals because p's always come in sets of 3. So I can have 2, 4, 6 electrons. The 5d sublevel, d's always come in sets of 5. Each one can hold 2, so I could have 10. The 4p sublevel again has 3 orbitals, so I could have 6 again. Notice that it didn't matter which principal energy level I was in. The p's come in sets of 3, and so I'll have 6 electrons that can fit. The other part I talked about was electron spin. Electron spin literally is that the electrons are spinning on an axis, and anytime you have a charge that is moving, it sets up a magnetic field. And so if the electrons that are in 1 orbital, you can fit 2, if they have opposite spins, that means their magnetic fields will be opposite, which will allow them to be in there together. It's kind of like when you have 2 magnets, if you align them in the same directions, north to north and south to south, they will repel quite a bit. But if you arrange them in opposite directions, the magnetic fields will stick and be favorable, and that will allow 2 electrons to fit in 1 orbital. So the way we draw that is that the arrows represent electrons. The circles represent an orbital. The up and down represents the spin. And of course, we label the sublevel with the principal energy level and the orbital type.